Until the early part of the 20th century, it went without saying that the matter we see is most of the matter there is. That would be protons and neutrons, with accelerating electrons creating the light we see. But that came into question in the early 1930s when Fritz Zwicky, a Swiss astronomer out of Caltech, studied the Coma cluster 321 million light-years away, with 1,000 galaxies spanning 25 million light-years in diameter. He looked at it in a number of ways, two of which are very revealing. In one, he used galaxy motion to calculate mass, and in the other, he used galaxy luminosity to calculate mass. His processes are not precise, but they do provide ballpark figures for the mass of the cluster. For motion, he had the cluster galaxies' radial velocities from the Doppler shift in the light we see. He then generalized them into their three-dimensional velocity dispersion statistical equivalent. This galaxy motion gives us the kinetic energy for the cluster. Zwicky used the well-understood virial theorem that has the kinetic energy of a system equal to 1/2 its gravitational potential energy. This allows us to solve for the mass of the cluster. This is the mass as measured by its gravitational effects. The second way he calculated the cluster's mass was to use the cluster's luminosity. You may recall from our discussion on the Hertzsprung-Russell diagram in our How Far Away Is It segment on distant stars that there is a relationship between a star's mass and its luminosity. We can use that relationship to estimate the mass of groups of stars by measuring their luminosity. We use the mass-to-light ratio of the Sun as the base for comparisons. Zwicky measured the luminosity of the average galaxy in the Coma cluster. Using a mass-to-light ratio of 3, he calculated its mass. When he multiplied the average times 1,000 galaxies in the cluster, he came out with a number that was over 100 times less than the mass calculated via the virial theorem based on gravity. In other words, the motion of the galaxies in the cluster indicated a mass that was over 100 times the mass from luminous matter. Zwicky concluded that either the laws of gravity as we know them, Newton's and Einstein's, did not work for volumes as large as the Coma cluster, or the luminous matter is only a very small part of the total matter of the cluster. He called the rest of the matter dark matter, and suggested that gravitational lensing could help quantify this dark matter. But back in the 1930s, nobody believed him. With this new understanding about the possibility and impact of dark matter, astronomers turned their attention to galaxy clusters like the one studied by Zwicky in 1936. Our case-in-point galaxy is known as the Bullet cluster. The virial motion of its galaxies indicates that a collision has occurred. Two massive clusters have passed through each other millions of years ago, and member galaxies are now flying apart. If we zoom in a bit closer, we can see the telltale arcs of more distant galaxies lensed by the gravity of the Bullet cluster. Counting the lensed objects and the estimated amount of light bending involved for each one, a map of the area containing most of the mass of the cluster can be superimposed. We have used blue to indicate the locations where the vast majority of the matter must be located in order to get the observed lensing. Here we have the cluster's hot X-ray emitting gas detected by the Chandra X-ray Observatory. The two pink clumps contain most of the normal matter, sometimes referred to as baryonic matter, or matter made up of protons and neutrons. The bullet-shaped clump on the right is the hot gas from one cluster, which passed through the hot gas from the other cluster during the collision. When we superimpose the dark, baryonic, and visible components of the cluster's mass, we get the full picture. The galaxies and the dark matter have traveled a great deal further than the gas. This indicates that the galaxies and dark matter in the two colliding clusters did not interfere with each other. In other words, they passed through each other without slowing down. On the other hand, during the collision, the gas clouds were slowed by a drag force, similar to air resistance. This combination had the effect of separating the gas from the dark matter. This separation is considered to be direct evidence that dark matter exists. Measurements indicate that the galaxy clusters on average have 85% dark matter, 14% intergalactic gas, and only 1% stars. In 2014, a team of astronomers found a supernova in this galaxy cluster, over 5 billion light-years away. The supernova actually happened in a galaxy 4 billion light-years beyond that, making it 9 billion light-years away. The huge mass of the foreground galaxy and galaxy cluster bent the light from the distant supernova, creating 4 separate images of the same explosion. The images are arranged around an elliptical galaxy in a formation known as an Einstein cross. Following this discovery, astronomers modeled several possible gas and dark matter distributions in the galaxy cluster. Each model predicted that another image of this supernova will appear in the cluster, but they had different time estimates ranging from 2015 through 2025. In December 2015, it appeared. For the first time in history, the time and location of a supernova was accurately predicted. We actually saw the supernova happen. Instead of detecting a flash in the sky and turning telescopes to its location, we had the telescopes already focused on the correct area and recorded the event from beginning to end. This was powerful evidence for dark matter. In the late 1920s, Edwin Hubble discovered that except for a few nearby galaxies, all galaxies were moving away from us, and the further away they are, the faster they are moving, along with the assumptions that there are no preferred places and no preferred directions in space. This means that all galaxies, not bound together by gravity, are moving away from each other. The flow of all galaxies away from each other, with faster velocities the further away from each other they are, cannot happen in a fixed volume, because in a fixed volume, some reference frames would have to have distant objects heading towards them for others to have them moving away. It can only be explained if the space that these galaxies exist in is itself expanding. Here's a one-dimensional example to illustrate why this is the case. Consider an 8-meter circle with marks 1 meter apart. If we are at the top mark and all the other marks are moving away from us, then, from other points of view, marks are getting closer. The system is not homogeneous. But if the apparent motion is due to the amount of space expanding, we get a different picture. Here, the marks hold their position on the line, but the line grows. Let's say each meter on the line expands to 2 meters over the course of a minute. We see that the distance between adjacent marks goes up 1 meter, and their apparent velocity, as seen by each other, is 1 meter per minute. But more distant marks have increased their distance and velocity by more than that. And the further away any two marks are, the more their distance and velocity have increased. And most importantly, this will be the same no matter which mark is used for the reference frame. In order to illustrate the point, this example uses an expansion rate that is 74,000 trillion times greater than the actual expansion rate as determined by the Hubble constant. The real expansion is very slow. If we take a look at what the expansion does to 1 meter, we see that it would take 1,000,000 years to expand by just 7/millionths of a meter. That's way too slow to ever notice or even measure in a lab in a lifetime. And it is why it's so easy to overcome it with local gravity out to the Andromeda Galaxy. It should be noted that this expansion of space itself does not pull apart objects that exist in that space. A meter stick does not expand. That's because the size of the meter stick is determined by the forces that hold it together, and these forces are not changing. Expanding space has significant implications for measuring distance. Here we are zooming into GN-Z11, the most distant object ever found. The galaxy's redshift, combined with Hubble's law, gives us the distance the light traveled, 13.4 billion light-years. And we know the speed of light, so the time traveled was 13.4 billion years. We normally say that the galaxy is therefore 13.4 billion light-years away. But during its long travel time, space expanded considerably. In fact, GN-Z11 was less than 2.7 billion light-years away from us when the light started its journey, and the galaxy is now over 30 billion light-years away. In order to calculate these distances, we need to know how the universe expanded during the light's journey. Note that if a galaxy is far enough away, its apparent velocity will be faster than the speed of light, and its light would never reach us. It would be beyond the physical visible horizon for the universe. It's not that it is moving through space that fast, it's just that more space is being created per second between us and them than light can traverse in 1 second. Plugging in the numbers, we find that all galaxies beyond 14 billion light-years could never be seen here. GN-Z11 is now 32 billion light-years away, so the light that is leaving GN-Z11 now will never reach us.